Good afternoon, students. Okay, so in the last lecture, we had started with call instruction, right? So we were looking into absolute call. Firstly, call instruction is used to execute a subroutine. Subroutine is a set of program which is required frequently for execution. Okay, and now absolute, there are two varieties of call. One is absolute call and the other one is long call. All the calls are unconditional, right? So we were looking into absolute call and long call. Absolute call is the subroutine should be available within 2 KB memory space, whereas long call, the subroutine can be anywhere in 64 KB memory. Okay, so students, we saw how does the microcontroller interact with the main program and the subroutine. While executing, when the call instruction is getting executed, microcontroller first obtains the return address. Return address mean the address of the next instruction to call. So in our example, it is 7801. This 7801 is called the return address. So while executing call instruction, this return address is saved on stack. Then microcontroller jumps to the subroutine. It means the subroutine address gets loaded in program counter, right? Then microcontroller executes the subroutine and then comes back to the main program, comes back to the return address 7801. And then it continues with the main program execution. So that is how there is interaction between the main program and the subroutine, right? This is how microcontroller executes the main program and subroutine. And we took an example of absolute call. So how is the format? Absolute call and mention an 11-bit address of the subroutine. Why 11-bit address? Because the absolute range is of 2 KB memory. Okay, so while executing call instruction, PC plus 2 means obtain the return address and then save the return address on stack. While saving, increment the stack pointer first, increment the stack pointer and then save the address. Now the address is 16-bit, stack is 8-bit. So the 8-bit address will be saved at a time. Is that okay? So increment the stack, save the lower address, then again increment the stack, save the higher address, and then the program counter gets loaded with the subroutine address. How is that subroutine address generated? 11-bit address from the instruction and the upper 5 bits remain the same. Okay, students. So we saw this was absolute call instruction. Now we will go for today we will see long call instruction, LCALL. Okay. So we will look into LCALL instruction. The format is LCALL and mention a 16-bit address of the subroutine. The subroutine can be placed anywhere within the 64 KB ROM memory. So mention the 16-bit address. Now, how many byte the instruction is? Since this is a 16-bit number, the instruction is 3 bytes. Correct. And since it is a program branching instruction, the time taken is of 2 machine cycles. So LCALL is a 3-byte instruction and the time taken is for execution is 2 machine cycles. So now, where is the return address? It means what is the address of the next instruction? See here, students. LCALL is a 3-byte instruction. So there are 3 memory locations required to save LCALL. So the next instruction will be 3 locations ahead. So what is the return at PC plus 3? So first obtain the return address. So microcontroller will increment PC plus 3. Okay. And now save this return address on stack. So whenever we are saving on stack, the pointer first increments. SP becomes SP plus 1. What is SP? Stack pointer. So stack pointer increments. And at this new location, the lower address is saved. Program counter, lower address is saved on stack. Again, the stack pointer increments by 1. And at this new location, higher return address is saved on stack. PC 15 to 8 mean the higher return address is saved on stack. And see, it is a long call instruction. Mean you have given a 16-bit address. So that 16-bit address as it is gets loaded in program counter. So 05FC is a 16-bit subroutine address. Correct? That gets loaded in program counter. Okay. So that is how these are the sequence of operations happen internally inside the microcontroller while executing the long call instruction. Okay, hope you all get me, students. So the same example, let us put some numbers and see how it works. So it is long call, right? And that 05FC. And I always say in those program branching instruction, mean if it is jump or if it is call, the programmer does not bother about the addresses. The programmer gives the label, right? So the way I will be writing the instruction is LCALL and some delay of the name of the subroutine. Here, delay is the name of the subroutine. Okay, so LCALL delay. That is how the programmer will write the instruction. Okay, whereas the assembler will find out what is the address of this subroutine, and accordingly it will insert that address. What is the subroutine address? 5FC. This will be automatically found out by the assembler and will be inserted in the instruction. As a programmer, I need not worry about the addresses. I just mention the label and the same label should be to the subroutine. I hope you all get me, students. So I'll be writing LCALL delay. Assembler will find it and make it LCALL 5FC hex. So these are the operations going to happen, students. Return address is at PC plus 3, right? So see here at 77FF, we have stored the LCALL instruction. Okay, so this is 77FF is a program memory address. So at 77FF, we have written LCALL instruction, LCALL 5FC, and 5FC is the subroutine address. Okay, so what all executions will happen? First, program counter will be incremented by 3. It means 77FF plus 3. So 77FF, the next number is 7800, 7801 and 7802. Correct? So 77FF plus 3 is 7802. So see what happens? Program counter gets loaded with 7802. Now we got the return address. That address is to be saved on stack. So this is the address of the next instruction in the main program. Now for saving on stack, stack pointer first increments. By default, stack is pointing to location 7. So then that address gets incremented. Stack pointer becomes 8. That's a new address. And at this new address, the lower return address is saved. So on stack, what is going to get saved? 02. What is the return address? 7802. Out of that 16-bit number, the lower number gets saved on stack 02. Okay. Now again the stack increments, pointer increments by 1. So stack pointer becomes 09. That's the new address, new location. And at this new location, the higher return address is saved. So 78 is saved on stack. Okay. And then what? The 16-bit number, subroutine address number is copied in program counter. So what is the subroutine number? 05FC gets copied in program counter. Correct? Here that modification does not happen. In absolute call, we give 11-bit address. So then that address gets modified. But in long call, the address is the 16-bit number itself. So that number is as it is copied in program counter. So now, whatever address program counter has, microcontroller will start executing instructions from that address. So from 5FC hex, the instructions will begin executing. So that's the subroutine. Hope you all are getting me, students. So that's how the program counter, the stack pointer, right, the stack memory is getting modified. Okay. So then we will see how does that stack get modified. Same example here, students. At 77FF, we have written LCALL instruction. And now let us see how is that stack memory getting modified. Okay, what is stack? It's a part of internal RAM memory. It begins from 7 hex. Okay, so now while executing this instruction, see what is going to happen. First, PC plus 3 mean program counter will become 7802. So that's the return address. This address is to be saved on stack. So now what is going to happen? Stack pointer will first increment. SP is SP plus 1. Means the new address is 8 hex. What will happen? SP becomes 8 hex. That's a new location. And at this new stack location, 02 will be stored. What is 02? The return address. The lower return address. Correct. So one address is saved. Higher address is still left. So now SP stack pointer again increments. SP is equal to S. That 2 is saved on stack. Correct. Now stack pointer again increments. SP is SP plus 1. So the new stack address is 9 hex. What happens? Stack pointer now, the address of stack pointer is 9. And at this new location, the higher return address is saved, 78. Correct? What happens? That 78 is stored on stack. Right? So the last filled location is 78. That is 9. The address is 9. So this is where your stack pointer is. And what operation is left now? This 16-bit number will be copied in program counter. So see, students, that's how the stack is getting modified. The stack started with 7. While executing call, the return address got saved on stack. So where is now new stack pointer? At location 9 hex. This is where is your stack pointer. Okay, students. So the operations happening internally are PC plus 3, increment the stack, save the lower return address, again increment the stack, save the higher return address, and the subroutine address gets copied in program counter. Now we will go for the return instruction. Right? We have two options, return and return from interrupt. Right? So if it is an interrupt subroutine, RETI, return from interrupt, should be written. Whereas if it is a regular subroutine, mean it's a delay program you're writing, right? Other than interrupts, you call them as a regular subroutines. So if there is a regular subroutine, the end instruction of subroutine is the return, RET. That's it, RET. Return from the subroutine. It is a 1 byte, 2 machine cycle instruction. What it is going to do? From that subroutine, microcontroller is going to come back to the main program. Okay, so RET, what does return instruction do? It stores the return address from stack into program counter. See here, students, where was my return address? 7802. See here on the right hand side. This 7802, what did we do? We had saved it on stack. While executing call instruction, the return address was saved on stack. Right? Now this return address is taken back. Right? 7802 is picked up from the stack and loaded in program counter. Who does that? The return instruction. The return instruction picks the return address from stack and copies in program counter. And that's the reason microcontroller returns back to the main program. Okay, so this stack 7802 will be read. Now while reading, what happens is read and then decrement the stack. So what happens? Wherever stack is pointing gets copied in program counter higher. Right? Look here students. This was a stack memory. What was the last location filled? 9 hex. What was there in 9 hex? 78. And what is 78? Higher address. Okay, so during return instruction, higher address is picked up and stored in higher program counter. So see here, SP double bracket mean the data pointed by stack pointer is picked up. 78 is picked up and stored in higher program counter. Okay, so this data is picked up. Right? Now which is to be picked up? 02. So the stack pointer has to decrement by 1. So what happens? SP is SP minus 1. Okay, so now the stack pointer initially was at 9. 78 was taken and stored in program counter higher. Now the stack pointer will come to 8 and 02 is picked up and stored in the lower program counter. So see here, SP minus 1 becomes 8 and the data from that 8 location, the number from that 8 location is picked up and stored in program counter lower. So that becomes 02. Okay, and the pointer again decrements by 1. So that now becomes 7. Here students. So with the help of return instruction, we come back to the original stack pointer 7 hex. Okay. Now let us see with an example. So RET. Remember stack pointer is at 9. Okay, remember what is my reference now? SP is at 9. Okay, and where did I write the return instruction? At 9000. So what will happen first? Where is SP? SP is at location 9. What is there at location 9? 78, upper address. So this upper address 78 is picked up and stored in the upper program counter. Next, stack pointer decrements by 1, means stack pointer becomes 8. So you're coming down. And whatever is at that location 8, that is read and stored in the program counter lower. And again the stack decrements by 1. So stack pointer comes back to 7. Okay, right? So finally program counter, what will you get? The return address. Initially 78 was picked up and then later on 02 was picked up. Where did this get saved? This got saved in program counter. So once the program counter is stored with 7802, microcontroller starts executing the instruction at 7802. And what is 7802? The main program address. The main program return address. Okay, students. So see, we will see with respect to stack. Okay, the same instruction was written at 9000, right? So what is stack pointer initially? Stack pointer is at 9. What is stored at 9? 78. This was already done by the call instruction. Now microcontroller is executing the return instruction. So stack pointer was at 9 and was pointing to 78. Right? Now this 78 is picked up and stored in higher program counter. Okay, students? This is reading the stack. Read 78 and save it in program counter higher. And now the stack pointer decrements. SP is SP minus 1. So it will come down. Stack pointer will now show 8. What is there at 8? Stack pointer will show 8. What is there at 8? The lower address 02. So 02 is picked up and stored in lower program counter. So this data is also read and the pointer again decrements. SP is SP minus 1. So what is the new address now? 7. Right. So what is the new address now? Stack will now point stack memory will now show 7 hex. Right? Stack pointer will show 7 hex address. Okay, and that's how program counter gets stored with 7802. So that's the main program instruction. Okay, students. So this is how the return instruction works. So remember always, whenever some data is saved on stack, pointer first increments and then the data is saved. Again increment, save the data. Again increment, save the third data. Whereas whenever we read from stack, first read and then decrement the pointer. Read the second data and then decrement the pointer. And it's a sequential access memory. Remember always. And what sequential access? LIFO. Last in, first out. Okay, have you all heard this word? FIFO, first in, first out. LIFO, last in, first out. Are you all familiar with this? Yes, yes. Right? So how is the stack here? Stack is the last entered data should be read first. So what was the last entered data? 78. So read 78. Then read 2. And that's how. Okay, so please remember, stack is sequential access. And what sequence of access? Last in, first out. Okay, can anyone tell me an example of first in, first out, students? Q, very good, very good. So Q is an example of first in, first out. Very good. Okay, so that is related to return. Now we will go to RETI. Now that word, that letter I indicates interrupt. Return from interrupt subroutine. Okay. Now see, the functionality is the same as that of the return instruction. The only difference is RETI enables all the interrupts, pops the return address from stack and saves it in program counter, right? So taking the return address from stack is done by the return also. So reading is also called as pop. Writing to stack is called as a push, right? So hence that word is used. What does RETI do? Enables all the interrupts and pops the return address from stack, saves it into program counter. And that's how it returns to the main program. Okay, see what happens, students. Whenever an interrupt arrives, microcontroller stops the current execution and jumps to interrupt service routine. And as soon as it jumps to that interrupt service routine, it automatically disables all the interrupts. Till the subroutine is completed, all the interrupts remain disabled. Correct? Are you getting me? So whenever an interrupt arrives, microcontroller is executing the interrupt, executing the subroutine interrupt. The interrupts are disabled by default. Right? It executes the subroutine, and at the last instruction, I should be writing RETI. And this RETI will enable the interrupts, take the return address from stack, and come back. If I do not write RETI, I just write RET. Then microcontroller will come back to the main program, but the interrupts will remain disabled. Are you getting me? Right? If I do not write that letter I, interrupts will not be enabled. They remain disabled. RETI will enable it. Okay. And take the return address from stack. How do you read from stack? Pop. How do you pop from stack? Read the stack. Save the higher address in higher register. Decrement the pointer by 1. Read the second address. Save it in lower register. And again decrement the pointer by 1. Right, students? So that's how it is Okay, that's how the call and the return instructions operate upon. Okay, now with this, hope you all have understood this. Now with this, we will go to how to write a subroutine, right? We will see one small example of writing a subroutine. Okay, students. So we will take an example of writing one LED blinking program, and we will make use of one function. Okay, so we will just take an example of writing a program to blink an LED. Okay, so let me start with, now see, LED is a 1-bit device. It is an output device, and one single LED mean I need logic 1 and logic 0 to turn it on or turn it off. So LED is a 1-bit output device. Okay, so then LED blinking, what comes in your mind? I want to see that LED blinking mean it should be turned on and then it should be turned off. So I start with the program org000. Okay, and then I sjmp to somewhere next, and then I write the label next. And what did I say? LED blinking means turn on the LED and turn it off. So turning it on, we didn't do this instruction, but then let me write set bit. Let me assume LED is connected to P0.0. Right? So what am I doing? I'm assuming this is where LED is connected. LED is connected to P0.0. So turn on the LED, and what am I doing it here? Turning it on. So turn it on and then turn it off. So what do I expect? Let it be off. So clear. Whom to clear? P0.0. Okay, and then I say stop my program. So I say stop the program, right? SJMP, and I say stop, and that label stop should come to the same instruction. Now there are modifications, students. I'm just writing the way we just thought of, and then I'll be writing the end directive END. So LED blinking, turn it on, turn it off. So we started with 000. We set the bit, we clear the bit, and we stop. There are many problems in this. We will see one by one. Right? Now, so the first thing is, see, I have set the bit, and immediately next I have cleared the bit. This is taking one machine cycle to execute. This is taking one machine cycle to execute. One machine cycle means 12 clock pulses. How much is the clock? 12 megahertz. Mean how much time is taken to execute this instruction? 1 microsecond. So setting the bit will happen within 1 microsecond. Again, clearing the bit will happen in another 1 microsecond. Right? So that on and off is going to happen at a rate of 1 microsecond. Will I be able to see that LED blinking? Right? 1 microsecond means 10 raised to minus 6. If that on and off is happening in 1 microsecond, will I be able to see that? Right? Right? Someone, can you all answer? No. Right? What change can we see? Do you all know persistence of vision? Anyone? What is persistence of vision? It is 1/10 of a second. Our persistence of vision is 1/10 of a second. What does that mean? If any changes happen in 1/10 of a second, we are able to recognize it. If anything happens faster than that, our eyes cannot detect it. Correct? So that is called persistence of vision. And here it is in microseconds. Will I be able to see that? No. Right? 10 raised to minus 6. Something is happening 1 upon 10 raised to minus 6 times. I will find that LED is continuously on, right? So that changes are not detectable to our eyes. So like this, setting and clearing all of a sudden, one after the other is not going to work out. Okay, then what then I have to do? I have to turn it on and I have to wait for some time. I have to keep it on for some time. Correct? I have to do something like this. Make it on and wait. Right? Then turn it off, and then again wait. I have to do something like this. And this wait, normally this wait should be 1/10, greater than 1/10 of a second. Right? Greater than GREATER, greater than 1/10 of a second. Then and then only I will be able to see that it is on. Again turn it off, wait for 1/10 of a second. Correct? So then I will be able to see that on and off. Right? So that one problem is gone. Now I'll be able to see that on and off. Right? But then I want a blinking. It should be continuous on, off, on, off, on, off. But the way I have written my program, set the bit, wait for some time, clear the bit, wait for some time, and stop. So will I be able to see the blinking? No. Correct? Will I be able to see the blinking? I will not be able to. It will only happen once. On, wait, off, wait, and stop. I want it to happen continuously, mean that on, off should be in a loop. Yes or no? It means this label should not be here. Correct? What should be the label? S jump. Where to go? Set the bit, wait, clear the bit. Again, set the bit, wait, clear the bit. It means what should that label be? That label should go to NEXT. On, off, and it will go on. Is that okay? So the second problem is also gone. I'm getting blinking. Right? But then what is this wait? Wait is not an instruction. I have to write something, right? I have to write something that microcontroller will spend time in between the on and the off. Right? So what is this wait mean? Generally, what do we do is, right? What do? We load some count in a register. So move R4, hash 0 FFX, and we keep on decrementing that. So DJNZ, whom to decrement R4, where to jump at the same decrement location, right? So where to jump, keep on decrementing till that R4 becomes 0. Correct? Hope you all are getting me. So this is what I should write. Mean microcontroller will unnecessarily keep on decrementing R4, FF, FE, asa karat 0, and once it is 0, it will come out. So that's what microcontroller is spending time here. And then after that, it will come out and clear the bit. So the same instruction should be written. The same thing should be written here. Are you getting me? So MOV R4 DJNZ, and the same instructions MOV R4 DJNZ. And see, the label should not be repeated. So here one, the labels, same labels आले नहीं पाहिजे. Correct? And now my program is done. Okay, but then that's not a good programming. See, the same instructions MOV R4 DJNZ R4, MOV R4 DJNZ R4, and suppose I need something this again. How many times am I going to write the same? That's a bad programming. Correct? Writing the same instructions again and again is a bad coding. Your memory size will unnecessarily increase. How much ROM do you have? 4 KB fakta. The internal memory is very, very small. So we should avoid repetitive instructions. The same instruction should not be written again and again. Then how do I do that? How do I do that is, I write that as a function. So see here students. So what will I do is, I will write that as a function. So this sjump next, I will write it here, right? Sjump next, and then mov r4 djnz r4, I will write it as a subroutine, right? And I'll give the name to my subroutine as wait colon. This is the name of my subroutine, mov r4 comma ff, decrementing r4 till it does not become 0, it remains in this, and as soon as it becomes 0, it will come out. So that's my subroutine. And what should be the last instruction of subroutine? RET. Okay, so this I'm highlighting it in red is my subroutine. And then whenever I need the subroutine, I will call. So either write LCALL or ACALL. So LCALL, and whom am I going to call? Wait, that is the name of the subroutine. Correct? Whenever I need that delay program, I'll just call by its name. So set the bit, call the delay function. Let me take this as a comment. Clear the bit and call that delay function. Right? So set the bit, call the R4 decrementing R4 program, clear the bit, call the decrementing R4 program, and let this repeat. So the one in black is the main program and the one in red is the subroutine program. And now the program ends. So after writing the subroutine, write the end directive. So that's how we write functions. How do we write function? Give some label to it. Like in my case, WAIT, give some label to it, write the function. The last instruction should be RET. And whenever you require this, say, so whenever you all require this WAIT, you just use the label. Okay. Now, one more thing is left. See, that call instruction, that return instruction is using stack memory. Yes or no? Right? Is using stack memory. Where is stack? The stack memory is starting from 7 hex. The stack memory is starting from 7 hex. And that 7 hex is also address of register R7. Bank 0 R7 register is nothing but the memory location 7. So then now there is an overlap between the register, the bank memory and the stack memory, which we do not want. Right? Are you getting me? If I do not, stack pointer is not mentioned anywhere. See here, students, in my program, SP is nowhere mentioned. It means SP will begin from 7 hex. And if I allow this to happen, the bank memory and the stack memory is getting overlapped. Okay. So to avoid this problem, what do? The stack memory is allotted at the last locations of internal RAM. How is my internal RAM? 00 to 7F. Correct. So 7F is the last location. So the stack memory is deliberately kept at the last locations. So usually 50 hex onwards, 60 hex onwards, 60 to 7F, right? Or 50 to 7F. It should be mentioned in the program. Okay. So what is done, students? Whenever that LCALL, whenever we use return, push, pop, or interrupts, the first instruction should be, right? Always, what should be the first instruction? Initializing stack, MOV, SP, comma, hash, and the last addresses, 50, 60, and so on. This is called initialize the stack memory. What is this called? INI, just a minute. INITIALIZD, initialize stack memory. From where? From 50 hex. From 50 hex onwards. Okay. Right. Now that bank and that stack memory overlapping is gone. So never forget this. Never forget initializing the stack pointer whenever you're using call, return, push, pop, and interrupts. Right? Are you getting me, students? No? That's how we do LED blinking. Right? The first thing is what? The rate. The blinking rate is very fast. So we slow it down. How do we slow it down? Turn it on and keep it on for some time. Turn it off. Again, keep on waiting for some time. That's how you slow down the blinking so that you will be able to see. It should be blinking mean that on and off should be in unconditional loop. Right, students? That on and off should be in unconditional loop. So S jump next. Now, yeah, just a minute. So I see S jump next. I need not initialize the stack pointer again and again. Okay, students? So initialization should happen only once. So let me write some another label, and that another label will go to what instruction? Set the bit, clear the bit. Okay. So S jump, that's an unconditional jump, unconditional loop where set the bit, wait, clear the bit, set the bit, wait, clear the bit. Okay, right? So the second problem was continuous blinking. So unconditional loop, S jump up, right? And instead of writing the same instructions again and again, I did write it as a subroutine. Give the label to the subroutine. The last instruction should be RET. And whenever you want to use the subroutine, use the same label, wait, wait. Right? And this is done, right? Now we will just execute this program and see, students, and then we will stop. So I just copy this program. Okay. And just a minute. We will execute it and we will stop. Okay. So let me open KEAL Microvision software. So hope you all are able to see KEAL Microvision. Hopefully, yes. Okay. So let me project new. So I will give a new folder, blink, B-L-I-N-K. B-L-I-N-K, blink. And I'll give the same name, B-L-I-N-K. It is asking me for the device. So microchip 89C51. 89C51. Okay, no. Right click target, output, create hex file. And now the new file, and I'll just paste it. We have already written the program, students. So file, save as blink.a. That's the program, assembly program. I will add existing file, right? And I will check for compile it, check for any errors, build target. Yeah, everything is fine. Hex file Ali, 0 error, 0 warning, and I'll run the program. Hope you all are there with me, students. Okay. So let me run the program, debug, start debug session. Okay. So we will start the execution. Now see where is it connected? P0.0. So it's a peripheral. So how will I see the answer? Up till now, we were looking the answer in the registers. We were looking the answer in memory location. Now, where will I see the output? On port P0.0. So before executing, go to peripherals. See, you have interrupt, IO port, serial timer. I need IO port and which port 0. So see, this window pops up. Can you see the parallel port 0? And there is tick, tick, tick. There is one is that pin row. And the other is P0. So the first one is the latch, and pins, wherever that pins is written, is the hardware pin, 40 pin. Okay, so you can see the two things. That's the P0 latch, and pins mean the 40 pins. And here I will be able to see that blinking. Okay, students? So let me execute. Now see which bit? P0.0. That is the last bit. P0.0. That tick will disappear. And that's how we will be able to recognize the blinking. Okay, so let me execute F11. So first is jump to the label next. Then stack pointer is 50. Then set the bit. That P0.0 already tick. Right, and now jump to subroutine. See students, it will jump to wait. Correct, subroutine jump has happened. R4, now first instruction, R4 is copied with FF. And now keep on decrementing R4, FE and so on. So I'm just pressing it. So see that R4 is getting decremented. 9, 8, 7, 6, 5, 4, 3, 2, 1. And now it is ED 8, 7, 6, 5, 4, 3, 2 and 0. So it came to return. And from return, it will come back to the main program. So F11, it came back to clear main program. And now clear that port. So see that tick is gone. P0.0, the tick is gone. And now then again it will jump to the subroutine. Wait. Load R4 and then keep on decrementing. So ED, CB, 9, 8. Students see here 6, 7. Hope you all are able to see the screen, huh, students? 2F. And then see that's C, 7, 4, 3, 2, 1 and 0. It will come out of decrement and it will return. And then it will again go back. It will again go back and set the bit. See that bit will be F11. Now I will directly run. See here students. Can you see the blinking? Everyone? See that there is a tick and untick coming here? Yes, yes. So, okay. So that's how we do LED blinking. That's how we write the function. Okay, students. Hope you all have understood this, students. Call, return, the LED blink program, and how to write a subroutine. Okay. Okay. So students, I'll stop here for today. Bye. Thank you. And see you in the next session.